Hi, welcome to Section 1.3. In the previous section we looked at sampling and random sampling methods. In this section we're going to consider the relationship or the differences between experiments and observational studies and look at some examples. I would suggest in this section, if you carefully read the section, you should be in good shape. Some of this material may be familiar to you from ideas you've encountered in science classes and in research, but I'll review some of the material and point you to some particular examples, as well as introduce some methods for R. I would remind you when you watch these in YouTube, if there are areas that are very clear to you and you want to speed ahead, remember in YouTube playback you can change the speed of the playback. So if I go on for 20 minutes, you can certainly make the playback go faster, and I assure you I won't be offended. I do that myself. Alright, so let's go ahead and get started. Just to set the stage, I want to recognize the two primary methods of data collection that we're considering in this section. One is the idea of an observational study. This is where we're observing individuals and measuring variables of interest without attempting to influence responses. And when I say individuals, we could be talking about people, could be talking about animals, we could be talking about plots in an agricultural or ecological study. Again, that's defined pretty loosely, context specific. Our purpose is descriptive. We want to understand the population that we're sampling from or measuring from, and we're usually studying associations. In some cases it's not feasible to experiment, and others this might be a preliminary stage where a second stage involves doing some sort of experimentation. Some examples of this would include health surveys, and by that I'm thinking of things like the NHANES study, NHANES study, which is a large-scale longitudinal study that's intended to represent the entire population. Another example is retrospective studies, where you compare, let's say, individuals with a disease versus those without, and you look back in time and see differences in behavior or risks that they were exposed to. And finally, perhaps field observations, where if you're going, let's say, out to the Arboretum and taking measurements from different types of areas, different tree cover, you're not imposing a treatment perhaps, but just looking to see how the response variable that you're interested in is related to some factor that you're able to observe. Second is an experiment. And in this case, of course, is a study in which the researcher actively controls or imposes some kind of treatment. They control one or more of the explanatory variables. And the primary purpose is indeed to investigate a cause and effect relationship. Famous examples of this would be the tests of new drugs, quite relevant now, thinking back to the 50s, the Salk polio vaccine trial, and I provided a link there in case you'd like to learn more about it. It was the largest public health experiment ever at the time, and some of the situations are reminiscent of what we're enduring right now. The other is some classic agricultural experiments from the Rothamsted Research facility in the UK. This was existent back in the 20s, if not before, but a lot of the terminology and early principles of experimental design come from work at Rothamsted Research. So there's a link to this, and I'll just take a quick look at that. Hopefully it will load all right. This is historic field experiments. You can see from the overhead a picture of very nice plots there that are used to study different treatments. There's some reference to classic experiments if you're interested in applications and in sort of these types of studies, perhaps in botany, agriculture. You can take a look on this electronic archive as well, so it's some fascinating information on historical experimentation. All right, now to move on and get in, I want to get in early, or sort of think early about the relationship between the idea of association and cause and effect. So Stephen Jay Gould is quoted as saying that the invalid assumption that correlation implies causation, cause, is probably among the 2 or 3 most serious and common errors of human reasoning. And I can't tell you the number of faculty meetings I've been in where a very educated person will lead with the phrase, "I know correlation does not imply causation, but..." Whenever we see a correlation or association, it's very tempting to want to make the leap to a cause and effect relationship, but we have to be extremely careful when we consider doing that. I want to focus on just a few examples first, and you can take a look at the details on these if you like. The wording around cause and effect studies, or the wording around studies and how results are sometimes communicated. For example, does the wording of the following headline imply a causal association? Physical activity improves cognitive function. And then you can take a look and see what you think. You might pause and consider whether that headline or whether that statement suggests a cause and effect relationship. And you can take a look at this study. It says regular physical activity can improve brain function throughout a lifespan. So surely they did an experiment. Well, you can take a look and you'll see in the first study, researchers found that young adults who run or participate preserve their thinking and memory skills for middle age. Second study found that people are physically active to protect themselves. So it was clearly an observational studies rather than experiments. So this idea of a cause and effect relationship is really not properly drawn from such studies. Another is, does the wording of the following headline imply a causal association? Exercise makes you smarter. Well, certainly exercise seems like a good thing, but whether this study can lead to conclude that exercise makes you smarter, well, I'll let you take a look and see what you decide. Here's another example. Physical activity linked to greater mental flexibility in older adults. Physical activity, we're certainly concerned with aging and your mental flexibility, so this is a reference to Science Daily. And here's a description. One day soon, doctors may determine how physically active you are simply by imaging your brain. And in this case, there's some work. We looked at 100 adults between the ages of 60 and 80, and we used accelerometers to objectively measure their physical activity over a week. And then they used functional MRI to observe characteristics of the brain and so forth. But it's, again, clearly not an experiment. And our study, when viewed in the context of previous studies that have examined behavioral variability in cognitive tests, suggests that more fit adults are more flexible, both cognitively in terms of brain function. Where the cause and effect is there, it still would be open to debate based on this particular type of study. Now, of course, it may be difficult to carry out an experiment to study something like this. I'll leave that again to you. Now, there's a classic set of literature from the 50s and 60s on the work to establish the relationship between smoking and lung cancer. There's a very good video here. Hans Rosling, who passed away recently, was a, I believe, Norwegian sort of data evangelist, one might say, and a very charismatic fellow. So there's a video here on relationship between smoking and lung cancer and establishing causation, and I would encourage you to take a look at that. They discuss some of the work of Richard Dahl in establishing that relationship and raise some important points that I'd like you to be familiar with. So clearly, one of the things that comes out of this is that association is not causation. Certainly now in retrospect, or in hindsight, we can see that smoking is clearly linked to lung cancer, but at the time the tobacco companies would refute any of the observational studies by saying that they had not established cause and effect relationship. So it's a pretty high bar to establish cause and effect relationship. Here's a suggestion for how one could establish cause and effect relationships. Two variables are associated if the values of one variable tend to be related to the values of the other. That's what we mean for association. To establish that they're causally associated is indeed the higher bar. If changing the value of one variable influences the value of the other. So first we'd have to see temporal precedence. That is, the cause should come before the effect. So the smoking would come before the lung cancer rather than the lung cancer before the smoking. Covariation, A implies B, not A implies not B. So smoking implies lung cancer. Stopping smoking means you're less likely to get lung cancer. So we need to be seeing that as well in observational studies. And there's no plausible alternative explanation. That is, any other explanation falls short of the supposed link that's being considered, right? That there's not another explanation, and that becomes difficult because how do we define plausible? So there's always room for discussion. Here's another example, exercise in the brain. A study found that elderly people who walked at least a mile a day had significantly higher brain volume and significantly lower rates of Alzheimer's and dementia compared to those who walked less. Well, what did they actually do in the study? Well, the article states that walking about a mile a day can increase the size of your gray matter and greatly decrease the chances of developing Alzheimer's. Did I just repeat myself there? Well, I'm sorry if I did. You can take a look at the details of this study, but the headline that ran on MSNBC.com quite some time ago now, but was that one way to ward off Alzheimer's, take a hike. And indeed, that's really not the conclusion that can be drawn here. Although it may be generally said that that would be a healthy thing to do, but it's not a cause and effect relationship that could be deduced. Here's a study that was in the headlines a few years back. Relationship between dental x-rays and cancer. And given that all of us have experienced dental x-rays, caught my attention, as well as a lot of other people in the NBC News. The lead sentence was, getting frequent dental x-rays appears to increase the risk of a commonly diagnosed brain tumor, a new study finds. Well, clearly this is not going to be an experiment. This is an observational study. There's an abstract we can take a quick look at to see what was actually going on here. So the methods, this was a case-controlled study including 1,433 patients who had intracranial meningioma diagnosed at ages of 20 to 79 years and were residents of the states of Connecticut. A control group of 1,350 individuals was frequency matched on age, sex, and geography. The main outcome measure for the report was the association between a diagnosis of an intracranial meningioma and self-reported bite wing, full mouth, and Panorex dental x-rays. So the problem with a study like this is it's relying on people's memory of what was done. And so when you have a brain tumor, perhaps there would be the tendency to overestimate how often you had x-rays if you thought there might be a link between those x-rays, or if you were being asked about something like that. So that's part of the discussion that was suggested, but still the conclusion was that exposure to some dental x-rays when performed in the past, when radiation exposure was greater than in the current era, appears to be associated with an increased risk of intracranial meningioma. And the suggestion was to really not go ahead with just routine x-rays unless there was some specific indication. So a lot of interesting background on that to take a look at. So correlation does not imply causation, no matter how important the study sounds. To really establish that cause and effect relationship, there's no substitute for doing a carefully considered or carefully designed experiment. Of course, it's not always possible, so we have to resort to other means, and hence the discussion of how you establish cause and effect from correlation that I was talking about earlier. All right, I think this will be fine for part 1. I'll see you on part 2. Take care. Thanks for listening.